Hello, good people. This is Calculus Early Transcendentals by James Stewart, and we are studying applications of the derivative, and this is section 3.9 on related rates. Okay, so I might go rather quickly through the various examples that I have here because I want to present a lot of examples so that you feel confident in approaching other related rate questions. So far, the only type of application type questions that we have gone over is your instant rate of change question or the find the equation of the tangent line question. With your instant rate of change question, you're usually given a scenario and possibly a function, or you might have to come up with a function, but usually it's given data, and your process is take the derivative and evaluate the function at that point. So if you're asked to find an instant rate of change or find the rate at which something is changing with respect to time or with respect to some other scenario, units, for example, in marginal cost, it's take the derivative and then evaluate your derivative at a particular value. With related rates, though, usually the data that you're given is you're given some data points, but then also another rate of a data point, and then asked to find a new rate. So if you're ever given a rate of change and asked to find another rate of change, you're dealing with a related rate question or a problem. And so I encourage you to follow the following steps in order to approach that related rate question. So let's read those rather quickly, and so that I can go over several examples and you can feel confident in approaching other related rate questions. So always with application problems, you want to read the problem carefully, underline any important information, and you might want to read it again and then read it a third time and figure out what is it that you need to find. And definitely look for, am I given a rate of change and asked to find another rate of change? Then yes, I'm dealing with related rates. Always draw a picture if you can. A lot of the times you'll have a picture that demonstrates a geometric figure like a circle or a sphere or a box or a right triangle, whatnot. But definitely draw the picture. Introduce notation, but definitely introduce notation. What do we mean? Variables. And it's okay to introduce more than one variable. That's fine. And note that usually with the rates of change, a lot of the variables are going to change with respect to time. Okay, so they'll be implicitly defined as functions of time. Step 4, express what is given and what we want to know in terms of the derivatives. Write an equation that relates the various quantities. So this is the point where you want to relate the variables. Okay, the variables that you're given. So you want to look at the shape that you're given and you want to see how can I relate the variables that I'm given in the equation. It says write an equation that relates those various quantities of the problem. If necessary, use the geometry of the situation to eliminate one of the variables by substitution. So sometimes you might have a third variable, but you're not given a rate for that variable. You usually only want to relate the variables where you have a given rate and ask to find the new rate on that new variable. And we'll come up with an example that has that. This step here in step 6, you're going to want to use implicit differentiation on every single variable in your equation because they're all implicitly defined as functions of t, usually. So you want to differentiate using implicit differentiation and the chain rule with respect to t. And then at the very end, after you have taken the derivative, just like with instant rates of change problems, that's when you go and substitute the values that you're given. However, backing up, sometimes you are given certain distances and stuff that will never change over time. Like if you've got two ships, or as we'll see in preceding examples, or an airplane is always flying at a certain height above the ground and it never changes that height above the ground, go ahead and use that height in your equation. Or if you've got a ladder slipping down the wall and that ladder is 10 feet, that ladder is always going to be 10 feet, so you can use that 10 feet in the problem. All right, so let's take a look at some of the examples so that we can approach these 7 steps. All right, and here we go. So in example 1 up here, and I'm looking at example 1 right in here. An oil rig springs a leak in calm seas and the oil spreads in a circular patch around the rig. If the radius of the oil patch increases at a rate of 30 miles per hour, how fast is the area of the patch increasing when the patch has a radius of 100 meters? All right, so I've got this circle because it says we've got an oil rig springs a leak in a calm seas and the oil spreads in a circular patch. So I've got a circle, and it also deals with a radius of the oil patch. And it says that the radius of the oil patch increases at a rate of 30 miles per hour. So if I actually call the radius r, then I can say that dr dt is equal to 30, right? And that would be miles per, or meters, or miles per hour. Is it miles per, or meters per hour? Good. And then it's asking me how fast. So whenever you see something that says how fast, that's asking you to find another rate. Good. So how fast is the area of the patch increasing when the patch has a radius of 100 meters? So they're asking find dA dt if we say define A to be the area of the circle, right? So they're asking find dA dt when, what does it ask you? When R is equal to 100 meters. Good. So how do I relate the variables? So if I'm going to relate the variables R and A, I know that A, looking at the picture that I have, A is equal to pi r squared because that's the area of the circle. Now I want to relate the rates, and when I relate the rates, I want to do implicit differentiation on both those variables. Okay, so what's the derivative of A? 1 times dA dt. What's the derivative of pi r squared? Pi times 2r dr dt, right? Because the derivative of a constant times a function is that constant times the derivative of the function, and we're also using implicit differentiation, which includes the chain rule. Okay, now that I have related the rates and I've already taken my differentiation, now it's time to sub my values. So I'm going to substitute my values, and I get dA dt is equal to 2 pi, and what is r? R is 100, and what is dr dt? 30. And now I can tell that dA dt, which is what I want to find, is going to be 30 times 100 is 3,000, and 3,000 times 2 is 6,000, and 6,000 times pi is 6,000 pi, and we have meters squared per hour. Good. Okay, so let's take a look at example 2 here. A particle moves along the hyperbola xy equal to 8 when it reaches the point 4,2, and that 4,2 is xy. The y-coordinate is decreasing at a rate of 3 centimeters per second. How fast? Again, we're asking how fast. That is, we are given a rate. And what is that rate? Given that dy dt. And I want to point out, if you're ever given something is decreasing, or you know that something is decreasing, you want to negate that rate of change. Or in other words, you want to say that this rate is equal to minus 3 centimeters per second because it's decreasing. Good. So given that dy dt is minus 3 centimeters per second, find dx dt. How fast is the x coordinate, right? And also given at xy equal to 4, 2, find dx dt. Good. And in this case, they've already given you the relationship between the variables. So in relating the variables, we already have that x times y is equal to 8. Good. So we don't have to actually draw the picture here, even though we have. They've already given you the relationship between x and y. So how fast is x changing when y is changing at that rate? So now it's time to relate the rates. And how do you relate the rates? You do implicit differentiation again. And when we do implicit differentiation here, x times y, we have to do the product rule. So the derivative of the first, which is x, is going to be dx dt times the second plus the first times the derivative of the second, and the derivative of y is dy dt, and then equal to the derivative of 8 is equal to 0. So now that we have related the rates, it's time to sub our values. And we're going to sub our values xy equal to 4, 2, and dy dt equal to minus 3, and we're going to solve for dx dt, right? So we have dx dt times y, and y is equal to 2, plus x is equal to 4, and y is equal, dy dt is equal to minus 3, and we know that that's going to equal 0. So we end up with 2 dx dt equal to, adding 12 to both sides, we get 12, and so dx dt is going to be increasing by 6 centimeters per second. Good. All right, moving right along. I'm going to skip this one for a second because it might be a little bit difficult. I want to move forward to example 4 so that we can get more comfortable with simple problems instead of ones that involve some geometry. All right. A 10-foot ladder rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? All right, so I've drawn the picture so far, and we know that the ladder is not going to change size, so it's always going to be 10 feet. But I also have that we've got a right triangle here, and so if I want to add some variables, I'm going to say that the horizontal line is going to be x, and the vertical line is going to be y. And let's just take a look at the other facts that we have. And it says if the bottom of the ladder slides away from the wall at a rate of 1 foot per second, I know that dx dt, since I called it x, dx dt is going to be 1 foot per second. And we know when it's sliding down, you know that that ladder is pushing away, so dx dt is increasing, right? And it's asking us how fast, again, so we're given one rate and we're asked to find another rate. How fast is the top of the ladder? So that's telling us find dy dt because that's what we want to find, and I labeled it y, so we're finding that rate of change when dx dt equals 1, and when the bottom of the ladder is 6 feet and x is equal to 6. Good. So what's our next step? Relate our variables. And what variables did I introduce? We want to relate our variables x and y. And I see a right triangle there, so think of the Pythagorean theorem. So I see that x squared plus y squared is going to equal 10 squared, right? Or 100. And now it is time to relate our rates. And in relating our rates, we want to do implicit differentiation. And so x squared is going to be 2x dx dt. Y squared is going to be 2y dy dt. That's our chain rule. And the derivative of 100 is 0. Now it's time to sub our values. And when we sub our values, we have x equal to 6. So what happens when x is equal to 6 and we have x squared plus y squared equal to 100? Then we would have 36 plus y squared equal to 100, and we would have y squared equal to 100 minus 36, which is 64, and so we would get y equal to 8. We kind of needed to go back to our original relation of our variables to get the other one, because we notice in our related rates equation that we need the value of y as well. So at that particular moment when x is equal to 6, what's the value of y, so that we still have that right triangle. So now I'm going to substitute those values, and x is equal to 6, dx dt is equal to 1. We have 2, y now we know is equal to 8, and we need to find dy dt. So now we're going to solve for dy dt, and I see 2 times 6 times 1 is 12. 2 times 8 is 16. I'm going to take the 12 and put it on the other side, and I'll have 16 dy dt is equal to negative 12, and so we'll have dy dt is minus 12 over 16, or minus 3/4 feet per second. Good. And that seems reasonable, since y is as if the ladder is slipping down the wall, y is decreasing, so we should have a negative rate of change. Make sense? Good. All right, do I want to do 5 or do I want to do 6? Maybe I want to do 7. Let's do 7 just to make sure that we have some stuff going on. All right. So here it says a 5-foot-tall woman walks at a rate of 8 feet per second away from a street light that is 20 feet above the ground. At what rate is the tip of her shadow moving? So what's the tip of her shadow? That's the tip of her shadow right over there. So I'm going to label some of these things. We know that the street light is always going to be 20 feet above the ground, so we know that this over here is going to be 20 feet. And we know that she is walking away from the street light, and she is 5 feet tall, so we also know that this is going to be 5 feet, right? And she's walking at a rate of 8 feet per second away from the street light. So if I actually call this distance y, I know that dy dt here is going to be 8 feet per second. And it's increasing, so it's going to be positive 8 feet per second. And it says, and so if I actually call this one dx, we actually want to find dx dt, because that's going to be the rate of the tip of her shadow. That's how much her shadow is moving. Good. So how can I relate my variables? That's probably going to use some similar triangles here. And we know with similar triangles are the same shape but different sizes. And we note that we do have the bigger triangle and the smaller triangle inside are going to be similar because we have the same interior angles, right? If we've got those corresponding angles and those are parallel, then the other angles, these angles are going to be parallel. So we're going to have these same interior angles. So we're going to have some similar triangles. So I can see that the bigger triangle is going to be 20 times y plus x. That's going to be similar to the smaller triangle, which is going to be 5 over x, right? So I can relate my variables with corresponding sides, right, are proportional. And if corresponding sides are proportional with similar triangles, I can see that y plus x over 20 is going to equal x over 5, right? And that's going to say, and I can rewrite that as 1/20th times y plus x equal to 1/5 times x, right? So that's related my variables, and now it's time to relate my rates. And so in relating my rates, I can do my implicit differentiation. That's going to be a constant times the derivative of the function, and the derivative of y is going to be dy dt, or 1 times dy dt. The derivative of x is going to be 1 times dx dt. And on the other side, I'm going to have 1/5, and the derivative of x is dx dt. Good, so that has related my rates, and now I want to sub my values, right? And so we want to, and then solve for dx dt. So I see here 1/20th, dy dt is going to equal 8. I don't know what dx dt is, but I want to find that. And 1/5, I want to still find dx dt. And now I want to clear my parentheses, and in clearing my parentheses, I get 8 over 20 plus 1/20th dx dt equal to 1/5 times dx dt. I might want to multiply on both sides by 20 just to get rid of the denominators. And in doing so, I end up with 8 plus dx dt equal to, and 20 divided by 5 is 4 dx dt. And so I end up with 8 equal to 3 times dx dt. And so I end up with 8/3. And what is this? What are the rates of change here? We've got feet per second. So 8/3 feet per second is going to equal dx dt, and that's how fast the tip of the shadow is moving. All right. So do we want to do some planes, or do we want to do some ships, or do we want to do some cones? Let's do some cones right here, and maybe that might do it because I don't want to have a very long video, but I want to do some similar triangle kind of stuff to help you guys with setting up your equations. All right, so here it says an inverted conical water tank with a height of 12 feet and a radius of 6 feet is drained through a hole in the vertex at a rate of 3 cubic feet per second. So we're given a rate of change, and it says what is the rate of change. So given a rate, asked to find another rate, it's a related rate question. And it says, what is the rate of change of the water depth when the depth is 3 feet? Good. So I've got a picture here of an inverted conical water tank, and we know that it is seeping out through the vertex. So we're slipping, or the water level is draining there. All right. So we've got 12 feet high and a radius of 6 feet, and it's drained through a hole in the vertex at a rate of 3 cubic feet per second. So we know that dV dt right is equal to 3 cubic feet, and it might negative 3 cubic feet per second, right? All right. And it's asking us what is the height, what is the water depth. So if I sit there and say H is equal to the depth of the water, it's asking us find dH dt when the depth is equal to 3 feet, and we know that dV dt is equal to minus 3. Good. So first we want to relate our variables. Okay, so if we're going to relate the variables h and v, my first thing is, well, I'm looking at a cone. I'm looking at the geometry of the cone. And what is the volume of a cone? The volume of a cone is 1/3 pi r squared times h. Good. But that's giving me 3 variables. I only want h and v in my equation, because I don't have anything about the rate of change of r. If I were given the rate of change of r, I could keep the r in there, and then when I did implicit differentiation, I could do the product rule on that. So I definitely want to, before I go and relate my variables, I want to get rid of that r. So how do I get rid of the r? Well, I notice again that I have some similar triangles going on, because I've got a right angle and a right angle here. And I can see that my bigger one on the outside, where I have 6 feet and I have the height of 12, is going to be similar to the smaller one of r with my h, right? And because corresponding sides are proportional, I can see that r over h is going to equal 6 over 12. So in solving for r, because I want to replace the r, I get r here equal to 1/2 times h. Good. So I'm going to substitute that value in here for r, so that I can get something that is entirely in v and h. So here I go doing that. My volume is 1/3 pi, and I'm going to substitute my 1/2 h squared times h. And in simplifying that, 1/3 times 1/2 times 1/2 is going to be 1/12. And I have h squared, but h squared times h is h cubed. So now I have an equation that is completely in v and h, and I have related my variables h and v. Now it's time to relate my rates. And in relating my rates, I do implicit differentiation. And so I take the derivative of v, which is 1 times dv dt, times pi. The derivative of h cubed is 3h squared times dh dt. Don't forget the chain rule on all of them. They're implicitly defined as functions of time. And now it is time to sub my values. And I'm probably going to add an extra page here so that I don't have to squeeze everything in there. So in substituting my values, I can say that dv dt is minus 3, and I have 1/12 pi times 3, and h, they said, was 3 feet also. And now I can find my dh dt. So I'm just subbing in the values that I have, and now I'm going to solve for dh dt. Good. So in seeing the, we've got 27 over 12, right? So we've got minus 3 equal to 3 times 3 times 3. That's going to be 27 over 12 pi times dh dt. And now I'm going to have minus 36 over 27 pi, right, equal to dh dt. And if I divide by 9 on the top and bottom, I get minus 4 over 3 pi is equal to dh dt. And height is measured in singular dimensions, so that's going to be minus 4 over 3 pi feet per second. And that's how much our depth is changing with respect to time at that moment. Good, so I hope you can see that the process is still the same. I hope that you can see in examples that we have gone over, you're given data and you're given a rate and asked to find another rate. So draw the picture, label the variables, take a look at the picture, and establish a relationship between the variables. Good. I think the last one that I would like to do, and then once you relate the variables and only the variables that you're given rates of change and asked to find the other rate of change. So like in that cone example, I wanted to get rid of the R because I didn't have a rate of change for the R. So that was helpful for me to do to get rid of that. So the final one here that I want to do, just because I want to give you guys more options on right triangles other than the Pythagorean theorem. So that's going to be the final one that I do, and I apologize if this video is a bit too long. Hopefully it's helpful. All right, so a plane flies horizontally at an altitude of 5 kilometers and passes directly over a tracking telescope on the ground. When the angle of elevation is pi over 3 radians, this angle is decreasing at a rate of pi over 6 radians per minute. How fast is the plane traveling at that time? All right. So we know that the plane is going this way, right? And we know that the plane is always going to be 5 kilometers. And it's going to go at that level. It didn't say it was going up or down, right? And we are given a rate, right? And we're given a rate that it's decreasing at pi radians per minute. And we're also asked to find another rate. How fast is the plane traveling at that time? So I see that we're given an angle of elevation as pi over 3 radians. So I'm going to say this is theta over there, right? And the distance between that tracking telescope and the plane is, or just that horizontal distance away, I'm going to say is x, right? And we know that the d theta dt is going to be decreasing, so it's going to be minus pi over 6 radians per minute, right? Good. And so if d theta dt is that, and we're actually asked, it says how fast is the plane traveling at that time, we're going to be asked to find dx dt, because that's the horizontal distance that the plane is traveling when the theta is equal to pi over 3, and of course d theta dt is equal to minus pi over 6. Good. All right, so what do we want to do? We want to relate the variables. And what variables did we introduce? We want to relate the variables x and theta. So I'm looking at that right triangle there, and I see a tangent, because tangent is opposite over adjacent. So I'm going to say that tangent theta here is equal to 5 over x, or in other words, 5 times x to the minus 1. Good, and now I don't have any extra variables in there, so I'm ready to relate my rates. So here I go relating my rates, and I'm going to do implicit differentiation, because both theta and x are implicitly functions of time because they're moving. All right, so what's the derivative of tangent? The derivative of tangent is secant squared theta, but then the derivative of the inside is d theta dt. The derivative of 5x to the minus 1 is minus 5x to the minus 2 times dx dt. Now I want to substitute my values, right? And what are the values that I have? I have d theta dt is equal to minus pi over 6, and I have that theta is equal to pi over 3, but I don't have the value of x. And so I want to find that value of x. And how do I find that value of x? I'm going to draw my triangle again, and I'm going to have that this is equal to pi over 3, right? Because that's my angle theta at pi over 3. That's 60 degrees. And you can either use a trig wheel or you can use that special triangle with proportion constants, which is usually what I do. And so my proportion constants are 1, 2, and root 3, because the side opposite a 30-degree angle is half the hypotenuse, and the 30-degree angle is the other angle. So I do know that I need to find secant of pi over 3, and so secant of pi over 3 is going to be hypotenuse over adjacent, and that's going to equal 2, right? And I also know that tangent of pi over 3 is supposed to be 5 pi over x, right? And so my tangent of pi over 3 is root 3. And so now I can tell that x here is going to be 5 over root 3. So I'm going to be taking the value of x equal to 5 pi over 3 and my secant of pi over 3 so that I can substitute my values. So my secant squared of pi over 3 times d theta dt, and d theta dt is negative pi over 6. Right, is going to equal minus 5, and I'm just going to take that x to the negative 2, and that x to the negative 2 is x squared, and so I'm going to put that in the denominator, and so that's going to be 5 over root 3 squared, and then we have dx dt. Good. And so what did I do? I subbed my values of theta, d theta dt, x to the negative 2, and that's why I needed to draw those triangles and say when theta is equal to pi over 3, what's my value of x and what's my value of secant, because I needed that in my related rates equation. So I know that secant squared of pi over 3 is going to be 2 squared, right? So this is going to be 2 squared. And we have minus pi over 6. And we have, I'm just going to write that a little lower. So we're going to have 2 squared times minus pi over 6 equal to minus pi, and then 5 over root 3 squared is 25 over 3 times dx dt. And now I'm going to solve for dx dt, right? So I am going to get minus 4 pi over 6 on that side, and if I divide, right, I'm going to get times, well, we're going to end up with minus 15 over 25, and this is minus 15 over 25, so if I multiply by 25 over minus 15 on this side, right, I end up with my dx dt. Good. And if I simplify my expression here, what do I get? Is that right? Do I get that? I get 3, yeah, minus 15 over 25. Well, I can simplify here, 25, 5, right? And 5 over here is 3. And I end up with here 3 and negative 2. Good. And then I have my minuses, and so I end up with that dx dt is going to be 10 pi over 9, right? And if it's an x, and x is a distance, it's going to be kilometers per minute. That's our unit of time. Good. Hopefully that is clear to you. So sometimes you're not always given all of the values that you need in the quote-unquote end game, always go back to the original relationship between the variables. And what was the relationship between the variables here? Tangent theta is equal to 5 over x. And so I was able to use that triangle to come up with x and come up with secant theta for that. All right, I think I've done a bunch of information overload for you guys, and it's time to call it quits. And I hope that you enjoyed yourselves and that you are confident in doing related rate questions. Draw your pictures, relate your variables, relate your rate.